So this is the first video in my journey of learning linear algebra. So I'm not sure how this is going to look like or work, given I'll be going through lots of text and YouTube videos. So to the audience, I'm not really sure how is this going to appear as or be of use anyways. But this is a way for me to commit, so I'm doing this anyway. I guess as we progress, we will figure out the best way to do this. Anyways, so I'm starting off with a book, Comprehensive Introduction to Linear Algebra, the same book I've talked about in the plan. So I usually like to go through the preface, so I'm going to do just that, like briefly skim through the preface. It gives you like a brief understanding of how the book actually works or how the book is structured. So from my understanding, all right, let's do this then. Intended for the upper division up undergraduate and beginning graduate students in mathematics. So this, I think this suits us quite fine. In a book which we hope we will still be referred to, which was a long time. So now, as a result, we have included formal material. Apologies about that. Seem to have several scripts running in the background. Some advanced topics of stencils and dimension vector spaces. So this is quite interesting. So this would actually help us to learn these two main concepts, tensors and infinite dimensional vector spaces. So given linear algebra is all about vector spaces, I guess this is a far more advanced topic. Elementary linear algebra, nice. Oh, I love this. I see this is intended for self-study, so they've structured the book in a way that the proofs are extremely detailed, and this is crucial. I mean, to me at least, I find it very important understanding the details of how things work rather than understanding, just the concept. Work out exercises, alright, that's good. Awesome. So in here, the talk is mostly about um, the authors are trying to address different backgrounds of students, the diversity of students, and where they're coming from. So you have engineering students, mathematics students, computer science students, and all of these different students might have had different exposure to the terminologies or the concepts introduced in linear that are going to be introduced in linear algebra. Um, so to combat that diversity or the variety in understandings, if that's the right term to use here. So to address that, the authors here had that in mind in writing this book, and that's why they've begun chapter 0 with the most elementary material needed to really understand the rest of the textbook. So this is very well thought. I mean, initially, this seems to be quite well-structured book, given they've considered the main two things we're lacking. So we're lacking the necessary experience you find in engineering students, mathematics students, and it also considers the fact that we might have introduced to similar concepts, but under different terms or terminologies or different, I don't know, different environment, different, different interpretations probably. It also has what he calls the self-study kind of structure. So we will be able to learn on our own. We don't have to, I mean, of course, we will have to go to different sources later on, but at least this gives us a kick start, a good kick start to um, get a good handle of things. Moving on. So in chapter 0, we'll basically start with abstract algebra. So the abstract algebra here, the necessary. So we got groups, unions, rings, fields, polynomials over fields um, that have a direct relationship to linear algebra. That's good. Uh, more advanced concepts as well, trivial concepts. Nice. So even the trivial things are introduced, and for those advanced students can simply skip through them. But I don't think we will do that in our case because we are still in the kindergarten level. P in slightly altered forms. The more advanced reader. So these details, what they are there. Nice. Thank you. I like this when they consider all different types of readers. I love it. Oh, I guess around chapter 8 and 11, this is where we will be introduced to the higher concepts. Well, of course, it's obvious, but the terms tensor and infinite dimensions that were mentioned earlier are actually explained in the third, I think is in the third part of this book. So we're still in the first part. Mm. Now, all these terminologies are quite advanced to us, so I'll skip through this. One major topic they have not treated is the numerical methods. So for the numerical methods, we will have to get acquainted to them in another book, another source, if so please. I think. Alright, now for one last comment on our notion, we use the symbol, I don't know, dimmed square, whatever, rectangle to denote the end of a proof. Oh, okay. Double front slash to denote the end of an example. Okay, so this means the end of a proof, and this means the end of an example. Sections are labeled chapter, section, exercise 2, 3, 4. Okay, so this is the typical form we see in textbooks. You just have to go back. I think I've missed something important here. There is little point in recommending a particle. Okay. So they don't regularly have a recommendation on an outline and a course outline. So this is basically. So in our case, it just applies that we just go through the different chapters and we get going. All right. So let's see what the foundation is all about. The first chapter. So we've got 7 sections, starting with sets, mapping, order, equals, relationship, cardinality. Now I understand these terms might look a little bit complex and high. Alright, looks like we've got introduction to groups. So we will basically start the actual stuff around chapter 2. So we can start off with the foundation now. I understand this is a bit slow paced, but I think as the moment we pick up the rhythm, we will speed up quite well. So let's jump to the first chapter, chapter 0. Chapter 0. I like how they gave the term 0 to the chapter. Start with the foundations. Alright. Finite dimensional vector spaces in sufficient detail. Understand and solve most linear algebra problems in mathematics and physics, likely to be encountered outside of specialized research. In other words, which are the general theory determinants matrix along with their relationship to linear transformations. It may be rather abstract since we feel already have a zero amount of experience in visualizing vectors in 3 dimensions. Further, we will discuss elementary concepts from analysis dealing with numbers and functions. Readers will probably be familiar with this material. It's worth summarizing the basic definitions that we will be using throughout this text. Ensure everyone is on the equal page here. Nice. So basically, I believe that this paragraph here means the book itself. It doesn't really necessarily mean that the chapter. Yeah, so this makes sense. I was a little bit concerned here when they start talking about the linear transformations and all. I figured, will they be jumping to these topics like early on? But it seems that it's just an introduction to the whole book. But this chapter is all about the foundation. So we'll begin with sets then. Now this is where the magic begins. This is the notion of a set of integers. Set is a collection of objects, each of which is called a point and alright, so one thing I would like to mention here is that we will be using so a friend of mine introduced me to what do you call spaced learning. So I'll be using the application I have on my phone just to remember these terms. Like, so the spaced learning basically reminds you of certain. It's like a Q&A. It's like flashcards, but presented in different time frames. So I think it's called Anchor. I'll be using my app for that. So I forgot to set up the desktop application. So I'll be setting that first. So we just copy and paste these new terminologies because we will be remembering them throughout the day. So anyway, so a set could be a collection of objects, and each element within the object is basically an element or a point. So it's like we have a set, a group, basically a group of objects. An object can be anything, could be an element, could be a point. Um, when you have integers, integers could be 0 plus -1, and so on and so forth. So no floating points with integers. And the set of integers denoted by these capital Z. So Z plus is only positive numbers, while the collection 0, 1, 2 is called a set of natural numbers or non-negative numbers. So Z plus is basically the same as positive integers and the same as natural numbers. And natural numbers are non-negative integers. If m and n does not equal 0 are integers, then the set of all numbers of the form m and n is called the set of rational numbers. So we have so what we've so we have three main things now. So we have the set and points and elements. I think this is basic. We have integers, which could be divided to. This is something we should note down. So we have the integers. This has positive integers, and then we have natural numbers, which is the same thing. So we can remove this. So it's positive integers, natural numbers, non-negative integers, right? Yeah, so instead of so this could be this would equal this would equal this. So from this, the set of so this is the full list of integers, positive and negative, and then z plus consists of the numbers 1, 2. So you see we don't have the 0 here. So the 0 is not part of this one, excluding the 0. Positive numbers, this exclude the 0. Okay, so the collection 0, 1, 2 is called natural numbers, non-negative numbers. This includes 0, includes the number 0, which is the natural numbers along with the it's basically the same terminology. If m and n does not equal 0 are integers, then the set of all numbers of the form mn is called the set of rational numbers. I think we need a little bit more introduction into what rational numbers are. Rational numbers, we have rational numbers here. Yeah, this is a good source. Dividing two integers. And what did it say here? N are integers, then the set of all numbers of the form N. So Mn is a fraction here. Okay, so the rational numbers is a set of fractions. So we have rational, different category, rational numbers. Like integers, like floats, result of fraction of integers. There you go. So we have m over n. That's the fraction form. So we can have this here. Now we will be adding all of these to, what do you call it? So we have different numbers. So this is this a rational number? Yes, it is, because it's 5 over 1. This is obviously a rational number, negative, still an integer, rational number, square root of 2, not a fraction, and hence is not a rational number. So better add, it is a fraction. It has to be fraction. A fraction. Float. That's fraction in linear algebra. Has a fraction form. We could add has a fraction form here. And we could add 5 over 1. Like 5 over 1. Irrational. Irrational numbers. So anything that has the form. So you see, I've said 1, 1, 1, 1 here. It's not right, because if it was a different number that has no fraction form, then you cannot say this being fraction. So like this one here. So irrational numbers, numbers that do not take a fraction form, like the pi, like square root of 2, or pi, 3.14, and so on. Alright, so going back to the textbook. So we're through the natural numbers, positive numbers, including the number 0. If m and n do not equal 0, so neither m or n are 0 and are integers, then the set of all the numbers of the form m and n is called the set of rational numbers, which we've seen being, and then you can denote here by this character, by this symbol. I'm not sure if we can copy these symbols. Latex, I think I called latex. Useless. I think if we've done Google Docs, we could have done something. Yeah, we could leave this here for now. I'll cleanse this later. So, all complex numbers. So we still have two more. So we have two more types of sets. We have the real numbers. We have real numbers, and then we also have complex numbers. If S and T are sets, then S is said to be a subset of T. Every element of S is also an element of T. Oh yeah, of course. That's S is a subset. No, X is a subset of S. X is a subset of T. The S does not equal T. The S is superset. Yeah. Let's see. So if T is the largest set and S is the smaller set, then S is a subset of T, given that every element in S is also an element of T. So we have X, which is an element in this set S. It means that that element is also in the set of T. However, if the sets S and T are not the same, then S is a proper subset of T. So it's a subset of T. We write S, this T, sometimes T. Okay, in this case T is said to be a superset of S. Ah, so if T is a superset of S, and this is a superset of T, then S equals T. Extremely useful in many proofs. The set of containing no elements at all is called and is denoted by an empty set. Interesting. Interesting. Subset. So if we go back to then we search for subset, we'll probably get visuals of this. I think, yeah, it's easier to look at this in a form of visuals. So we have A subset of B. Every member of A is part of B, which is we denote by the symbol, by the Greek symbol, which is what this term is. This term is right here. Now, let's introduction to sets. Yeah, there's an element of the set, and then we were acquainted with all integers, real numbers. Oh, okay. So there's almost always the real numbers. So real numbers is a combination of integer, floats, as in rational numbers, irrational numbers, integers, or maybe the irrational numbers could be in the complex set. So the complex set is more is a bigger set than the real numbers. Oh yeah, this is what we're looking for. You don't have to listen to the standard. You can use something like M to represent a set without breaking any mathematical laws. Watch out, you can get using math for dividing by zero. Of course, this notation is pretty nice and easy to follow, so why not? Let's see, A is a set of small letter A is a set of capital A symbol. I'm not sure what to call the symbol, but yeah. It's not a set, we use this. So assuming the larger set is A, 1, 2, 3, you can say 1 belongs to A, and 2 belongs to A, and 3 belongs to A. But 10 or 5 does not belong to A, using the symbol here. Fair enough. Now if two sets are equal, if they have precisely the same members, they may not seem equal, so you may have to examine them closely. So A is the set whose members are the first four positive whole numbers. So 1, 2, 3, 4. B is 4, 2, 1, 3. They both contain 1. They both contain 2. They both contain 3, 4. Every element of both sets. So yes, they are equal. So equal sets is when every single element within the set equals and matches the number. So A equals B. Fair enough. Subsets. This is where things get interesting. Set and a subset. So 1 and 6 is not a subset of B, since it has an element 6 which is not in the parent sets. Wait a second. So subset 1, 2, 3, which is I, capital A. Subset is 3 and 4. Even another one. Fair enough. Yeah. 6 is not in the list of elements within this set. So A is a subset of B if and only if every element of A is in B. Going through some examples here. So is A a subset of B where A equals 1, 3, and 4, and B equals 1, 4, 3, 2. Yeah, that's a subset. Yeah. 1 is a subset of B, 1 is in A, 3 is in A, 4 is in A. So yeah. 2 is in B, but not in A. But remember, that does not matter. We only look at the element. Yeah, of course. Let's try a hard example. Yeah. Let A be all multiples of 4, and B be all multiples of 2. Fair enough. So if you assume, let's just take like the first two numbers. So multiples of 2. We have 2, 4, 6, 8. And then this one multiples of 4. So we have 2, 4, 8. Yeah, it is a subset. I'll say it is a subset. We can't check every element in this set because there are infinite numbers of elements, yes. So we need to get an idea of what the elements look like in each and then compare. So we have these sets, negative 8, 4, 0, 4. Now notice here that we've used the negative along with the positive because it didn't specify that we have to only use natural numbers. So it says integers, but regardless of whatever. We're pairing off members of the sets. Now you realize that B has a larger so the intersection here, so all the elements that exist in A exist in B. Every element of A is also a member of B, but not every member of B is in A. Obvious. So A is a subset of B, but B is not a subset of A. Of course. Now, proper subsets. This is something we can find quite handy. If we look at the definition a lot, come to a weird conclusion. Let A be a set. Is every element in A an element in A? This is weird. Is every element in A an element in A? Well, yeah, of course, yeah. So doesn't that mean that A is a subset of A? Yeah. It does not seem proper, does it? We want our subsets to be proper. So we introduce what else but proper subsets? A is a proper subset of B if and only if every element in A is also in B. And there exists at least one element in B that's not in A. Now, this is interesting. A is a proper subset of B if and only if every element in A is in B. There exists at least one element in B that's not in A. So this is a proper subset. At the end is only there so that A is not a proper subset of itself. Otherwise, it's exactly the same as normal subset. If we take a look at the example, we have 1, 2, 3 is a subset of 1, 2, 3, but it's not a proper subset of 1, 2, 3. 1, 2, 3 is a proper subset of 1, 2, 3, 4, because the element 4 is not in the first set. Notice that if A is a proper subset of B, then it's also a subset of B. Yes, of course. Interesting. So I need to write all this down here. So the real numbers, complex numbers, can even host irrational numbers and numbers with power. Alright. Like this example. So we will use this example here. Example 2. Alright. Nice. So I'll cleanse all these notes later and have them in the mobile app I've told you about the spaced learning. So I'll add all of this in and make use of it. Alright, even more notations. Nice. So when we say that A is a subset of B, we write A is a subset of B. So you see the equal here, there is an equal sign, because this renders this example valid. So 1, 2, 3 is a subset of 1, 2, 3. It's like it equals its own self. It's duplicate, or yeah. That A is not a subset of B, adding the cross along the line. Talk about proper subsets. So a proper subset is that A intersects with B but do not equal. You take out the line underneath. Yeah, so this is intersection, so it means A is a subset of B, but B does not equal A. So, and A is not a subset, we just do a crossover. Now, this is probably the weirdest thing about sets. An example, think of this set of piano keys on a guitar. What? There are no piano keys on a guitar. And right you are. It's a set with no elements. So it's an empty set, it's a null set, presented by null set. Just an empty brackets. Some other examples, set of countries south of the South Pole. Yeah, I like this. Now this is another interesting bit. So let's go back to our definition of subsets. We have a set of A. We don't define it any more than that. It's just a set. It could be any set. Is the empty set a set of A? Going back to our definition of subsets, if every element in the empty set is also is also in A, then the empty set is a subset of A. But what if we have no elements? It's a proper subset. It takes introduction to logic to understand this, but this statement is one that is vacuously or trivially true. The good thing about it is we can't find any elements in the empty set that aren't in A. So A must be that all elements in the empty set are in A. So the answer to the post question is a resounding yes. The empty set is a subset of every set, including the empty set itself. Nice. Okay. So this basically the logic behind this is that we've looked at the duplicate sets or the um, identical sets. When we have a set identical to another, then we say A is a subset of another set. Like in this case, 1, 2, 3 is a subset of 1, 2, 3. Now with this definition, an empty set is a subset of its own, of the duplicate, what do you call it? An empty set is a duplicate or an identical set of another empty set. So they are both subsets of each other. Now, if we have another set that can contain the element, the empty set, it could be anything. So the definition says here that the subset, the empty element subset, is a subset of every set regardless, including the empty set itself. Okay. So quickly revisit this. So let's go back. We have a set A. We don't define it any more than that. It could be any sets. Remember if every element in the empty set is also in A, then the empty set is yes. But what if we have no elements? It takes the introduction to logic to understand this. Any element in the empty set that aren't in A. We can't find any elements in the empty set that are in A. So it must be that all elements in the empty set are in A. Okay. Now we need to check if let's try to Google empty sets. Try to Google empty sets, and then we want to add empty sets subsets. Just have a quick understanding. It's a subset of every set. Alright, looks like we have to. Now, so what I'm curious about is that, say I have 1, 2, 3. Isn't the empty set a subset of 1, 2, 3? Now, I've explicitly mentioned that it's not a subset. There is no empty set within the 1, 2, 3. So I'm not sure how is that going to look like. What you wrote is false. Well, perhaps what you want to show is that the empty set is a subset of every set. So there are probably many ways of convincing yourself or student that this is the case. The set A is a subset of B if and only if every element in A is also in B. We've already seen that. If A is the empty set, then A has no elements, and so all of its elements that are none belong to B, no matter what set B we're dealing with. That is, the empty set is a subset of every set. Another way of understanding it is to look at the intersections. The intersection of two sets is a subset of each. So is the empty set, and A is in a set, in any set then, which means it's a subset of A. By contradiction, let's say that you have an empty set and a set A. Based on the definition, the empty set is a subset of A unless there is some elements that are not in A. Yeah. It's not a subset of A. There is an element in the empty list, but the empty list has no element and has This is a contradiction. So the set must be a subset of A. Non-empty set might be this: the set of all women who have walked on the moon and the set of all the astronauts. Examine the three arguments above with this example in mind. So we have no women who've walked on the moon. Then we have okay. Alright, so say for example the set X and B. I don't see anywhere in X. So how, yeah, this is basically so similar to our question. That's because there are statements that are true. Means for all Y, we have Y. Yeah, now, is it true that for all Y, it's more like they're using the contradiction here. It's like the inverse. So when you're saying, say for example, in our example here, we have the set 1, 2, 3, 4, and then we have an empty list. Now, can you have an element in the empty list that's not in say A is the empty list and this is B. So in the empty list, is there any element in A that doesn't exist in B? Given it's an empty list, by default, no. So it's like A has no elements and there isn't an element that doesn't exist in B. So you get the points? Nice. So let's go with this answer here because it uses the notations, which I think will get us quite familiar with. We'll get used to this term. If we use the notations frequently, we will be more acquainted with how these terms work. So we have a Y subsets, it's a subset of X. So every element in Y exists in X and can be the same. It can be an identical. It can happen that these are identical sets, and only if there exists an element X where X belongs to Y, and X also belongs to X. Fair enough. Definition with empty list in place. Assuming empty list belongs to X if and only if X belongs to the empty list and X belongs to. Now you must use the truth table definition of yields. You have that if P is false, then P equals Q is true. For Q is whatever. This is not scoring subsets and also the elements of. No wonder this guy got the most upvotes, because this makes the most sense. Every element of the empty list is also an element of X. Or another, can you name an element in the empty list that's not an element of X? Because it's an empty list and you have absolutely nowhere to go. I love this. I think I'm I can put this in the cards. It's very easy. Nice. Our statements, they're very closely true. Belongs to X is for all Y. It's true then for all we have. Yeah, and this is also true because Y belongs and an element belongs to the set Y. We have the same element belongs to X, which is the intersection, or what do you call it? The subset, sorry. Now, it is true that for all Y that belongs to the empty list, if an empty list belongs to the empty list, then we have Y belong to the superset. This is very true. Now, you can't pick any Y. Now, I like this. This is also very nice. I'm also gonna now hopefully surprisingly it did work. The symbols did work. Alright, so this is the first lesson. So we have empty lists and then we have formulas, intersection. We still have a so this is on its I didn't expect to take this much time going through this. It's been quite some time since I've last been introduced to these. Now, this is really important because down the line you will be very we will get to see a lot of this, and it would make sense to, and it won't be easy to really understand the literature if you really can't understand these terminologies. With that said, I think the way we are going to do this is becoming more clearer. So we're going to cleanse this up and then add what needs to be added to the application I've told you about. And we'll have to revisit this like really super quickly and start with the video, the fundamentals of arithmetics, which this talks about the real numbers and stuff, so the things we've been talking about. So we will have to finish all of this, as in intersections and unions and joints and whatever. We have, when we are through with this and we hit mappings, I think we will be confident to say that we've came a really long way. Not really long way, but you get my point, right? So this is a journey and it's one step at a time. Alright, so until the next video, I'll finish the rest off camera, cleanse things, and you don't have to watch the rest. I mean, but this is basically the topic of today. We're talking about elements, real numbers, joints, and negative numbers, the unions, and how come an empty list is actually a subset of every set out there. So next we will have to talk about intersections, and yeah, I've also been acquainted with the empty list as well. So yeah, so I will just go through these examples of camera now and pose around intersections for the next video. Adios, folks.